So, hello everyone. Welcome. With Camilo here, we are going to present how to deploy a virtual IED on SEAPATH project. But first, I will let Camilo introduce itself.
Good morning. I am based in Spain, in Bilbao. I am part of GE Vernova. GE Vernova is a huge company founded by Thomas Alva Edison at the start of 20th century. We have more than 70,000 employees globally, and today we are supplying 25% of the power of the world. Okay.
And I am Erwann Roussy. I work at Savoir-faire Linux, which is a services company specialized in open source software. We work a lot with RTE since 2019 to create the SEAPATH project, and we work with the GE team of Camilo for 2 years. We're a member of the LF Energy and also the Yocto project, and the company works in several different subjects like robotics, avionics, healthcare, and today energy. So first I will describe SEAPATH as a project. The goal of SEAPATH is to provide an operating system to run virtual IEDs. So we are running on hypervisor, and on top of SEAPATH, on top of the code of SEAPATH, we'll run the virtual IEDs, which will communicate with all the protocol of the substation. I think you know better than me. The goal of SEAPATH is not to provide the virtual IEDs. It's not to provide any protection algorithm, UI, SCADA, I don't know. The goal of SEAPATH is only to be the operating system, the base on which the virtual machines and the virtual IED will be able to run. It means we provide them what they need: reliability, cybersecurity, resilience, and performance. All those type of things. So let me describe how to deploy a virtual machine on SEAPATH, and after that Camilo will describe what GE decided to put inside the virtual machine. But first, two definitions. I promise this will be interesting. We want to deploy real-time virtual machines. Real-time is a concept of computer science that it's not really well named. With real-time, we want to focus on response time. It means we want to be 100% sure to respond in a certain window of time. It is not a question of performance. It's a question of reducing the jitter between the different responses. It means we prefer to be less fast, but more deterministic. Virtual machine is a better name. It just describes a machine, so an operating system, all the kernel, the libraries, the applications. On the target application can be a protection algorithm that is not going to run on a physical computer like this one, but on a virtualized hardware. That means we have to simulate the disk, the RAM, the network interface, the CPUs, everything you need to be able to run this virtual machine. Now let's look what's inside SEAPATH. SEAPATH is an open source project, and it uses many already well-known open source projects. So we are Linux-based. We use Ceph and Pacemaker for redundancy, especially on the SEAPATH cluster when we have multiple machines. I will talk a bit about that later. We use OpenVSwitch here for virtual networking, so software-defined networking, especially the ability to deploy a network over multiple machines over a SEAPATH cluster. We use KVM and QEMU, which are standard tools to deploy virtual machines on Linux. And we use also libvirt as an API to just simplify the use and the deployment on virtual machines. Here is also Ansible, an orchestration tool that we use a lot on SEAPATH, but I don't talk about it today. Okay, let's start with how to provide virtual machines. Let's say I'm a protection manufacturer. I want to create virtual machines. What do I do? Where do I start? So there's two things to provide. The first one is the QEMU image. The QEMU image is the code of the virtual machines. It means it's the operating system. It's an ISO file or a QQ2 files that are two formats that are known. It contains all the kernel, all the services, and all the target applications. It means it contains the code of the protection algorithm you want to run. QEMU will be in charge of running this code. It means emulating all the hardware you need and running the actual code inside the virtual machines. The second part of that is what do we need as hardware? Because we emulate hardware, what does the virtual machines need? And that is a simple XML files, describe libvirt XML file, in which we described how many CPUs do we want, how many memories, RAM or disk, network interfaces, do we need a keyboard or USB key, I don't know. Everything is described in this file. It means if you want to deploy a virtual machine of SEAPATH, you have two main things to do. First, to create the ISO files that can be more or less complex, depending on which software do you have first, and then decide what hardware does your machine need. Especially, we are going to talk a lot about CPU and network in this presentation. I can give two examples to be more precise on what we do on SEAPATH, what we advise on SEAPATH regarding the hardware specification. The first is about memory allocation. Because we need to be deterministic, not really fast and efficient, but deterministic, we want to pre-allocate the RAM of the virtual machines at start. It means that if later the VM needs more RAM, everything is already allocated, and we don't need to ask more RAM to the hypervisor when the VM needs it. The RAM will not be used so often, but the question is, when the VM needs it, it's already there. We don't have to wait for it to come. And always that's the question of not be efficient and performant, but be deterministic. The second thing we do is putting QEMU at a real-time priority. That means we ask the hypervisor to run QEMU, which will run the virtual machines, like a real-time software. And we will do many optimization to be able to treat this process as a real time in order for it to respond with much determinism. Both things are done in the libvirt XML, just example to understand what is it for. For example, here we choose the scheduler of the QEMU process, the priority, and so on. Okay, now let's talk about the hypervisor architecture and what tool of Linux do we use to provide all the functionalities I have described before. First, network technologies. There are two main ways to provide network to the virtual machines. The first one is bridges. Bridges are basically virtual switch. So in our case here you have an hypervisor with network cards. And if a packet arrives, it goes into the network card, the physical network cards of the hypervisor. It goes into the bridge, so virtual switch, and this dispatched to the virtual machines. This is really efficient, but you have to go under all the hypervisor bridge and then inside the virtual machine. So you have two Linux to go in, or two operating systems to go in, the hypervisor and then the virtual machines. We have two types of bridges that we use. Linux one that only relies on the kernel, and OpenVSwitch one. Basically, OpenVSwitch is more advanced, has more advanced features, but is a bit slower. The second type of network technology we can use is physical access. Most well known is PCI pass-through. Here, basically, the VM takes control of the network card, which means we don't use the hypervisor kernel on operating system anymore. The VM, the packets is already passed into the VM. Another way to do that is with SRIUV. Main difference between the two is that PCI pass-through requires one interface per VM. You cannot use this interface for multiple VMs. With SRIUV you can, but you need a specific network card that is in fact higher in price, as always. Every card is compatible with PCI pass-through. With SRIUV you have to buy a specific card. Now we can talk about CPU. So you have a big CPU on your server, on your hypervisor, and you have many cores on it. How do you distribute these cores between the different processes? So first, you have to allocate the system of the hypervisor here. This is basically SEAPATH. This is the operating system. This is the Linux kernel, all the system services, all the software, so Ceph, Pacemaker, OVS that I already described, that are running on those specific core. They are isolated, so they will not be able to run on the other cores that we want to use for other purpose. The main purpose on the right is to run virtual machines. So what we do here is that we have CPUs, emulated CPUs and emulated cores inside the virtual machines, and we want to pin them, each CPU, to one physical core. The idea, and this is always for real-time virtual machines, if we need determinism, is to be sure that when the VM needs to run something on a core, no one will be there and nothing will stop it. The core is free for the VM to run anything she wants. So it's a bit of question, because most of the time, those CPU won't be used so much. But when the VM needs it, the core will need to be free. And so it's a huge question of how many cores you put inside your virtual machines, because it has a direct impact of how many virtual machines you can run on your hypervisor. The last one, the last core that we want to address is the QEMU cores, which is only needed when you run real-time virtual machines and network bridges. Remember when I talk about network bridges here, the thing is you have to go inside the hypervisor kernel to run the bridge. And this is exactly what this core will do. It will be dedicated to run this software. You don't need it when you use physical access, network interface, physical access. The thing is, what we discovered today is that you even need one core per VM when you use those type of technologies. If you want to be really deterministic, you will need to address these cores for all QEMU threads. All of what I described are also available in the libvirt XML, so we describe the hardware of the virtual machines. Just for the example, let's present a bit of performances of SEAPATH. Those are network performances. So what we measure in SEAPATH is between, we send sample value most of the time, between the emission of sample value and the reception inside the virtual machines. So basically we stop the measure when the protection begins. I do not talk about protection here. Camilo will talk about later. So we don't have 300 microseconds for protections. That's not the case. It's just the reception of the sample value, between emission and reception of the sample value. We can use different technology. Here I put two. With OpenVSwitch, we have a pretty good latency, maximum 300 microseconds. But the thing is, at a certain amount of load, it diverges. Here, 40 streams on the Advantech server that we use to run the SEAPATH, but it could be another thing on other Advantech. And we also need one core to use all the QEMU processes, as I described later, before, sorry. The PCI pass-through technologies is faster, as I said, 120 microseconds, but needs one card per VM. And here you don't have any limitation. The first limitation that you will see is the physical limitation of the network card that you use. So if you go above a certain amount, most of the time 1 gigabits, the network card cannot follow and you will have bad latency.
Let me add one thing here.
Yeah.
This is very important. This is very important because I don't know how much familiar you are with all the protection and control environment, but when digitalizing the analog values, okay, through a merging unit or something similar, we are collecting the currents and the volts every 250 microseconds. Okay, that means that the network infrastructure has to be strong enough to be as deterministic, okay, to be sure that you are able to collect and to parse every 250 microseconds the sample value frame. If you are not able to do that within those 250 microseconds, you are losing samples. If you are losing samples, your product is not secure. You cannot go to a real substation with a product that it is losing samples. Okay, and 250 microseconds is very, very critical. So you need true real-time performance to do that. Okay, so that is a very, very important topic.
Next performance test that we do is about PRP, so network redundancy. That's a parallel redundancy protocol. We test two things: hardware PRP that necessitates a specific card, and software PRP that is handled by the Linux kernel. Hardware PRP is good in terms of latency and throughput, no problem with that, but you need a dedicated card. Software PRP could be a good idea because when you only see the throughput, so the load, the number of streams you send, you don't have any impact, everything is received well, but in terms of latency, it is really bad. So here we did 2 tests with classic sending or hardware PRP, that's the same. And here with PRP enabled, we can see we have 10 times the latency in terms of latency reception. So last test I present. So we cannot use software PRP in SEAPATH. That's not possible for real-time virtual machines. Last but not least, time synchronization with PTP. We have 2 main ways to do that. First is we send PTP frames directly inside the virtual machines, and the virtual machine synchronizes itself with the PTP master. Or we synchronize the host, and the host using PTP KVM will allow the VM to synchronize itself. It will create a clock inside the virtual machines so it can synchronize itself. From experience, PTP KVM has proven to be more efficient to synchronize the VM, and we have a max deviation of 5 microseconds. So most of the time it's less, but max is 5 microseconds. Okay, now as the last part for me, let's talk about redundancy. So it's good to have a virtual machine, but how do we do if something fails? Anything can fail. The first idea we developed on SEAPATH is the cluster. Very simple, you have one hypervisor here, let's duplicate it and create another hypervisor here. We put VMs on 2 hypervisors, and using Open vSwitch, the extended switch, the extended bridge that I talked before, you can send sample values, and every machine on the 2 hypervisor will receive the same sample values. So basically, you can migrate your VM, you can start your VM on one hypervisor, and it can migrate on another without rebooting. So it's live migration, it's when the machine still runs when it migrates. For that, you need also a third machine that's just an observer. It's less powerful machine, but to be able to take decisions. The main goal is on the hypervisor. This is good, but has 2 main drawbacks. The first one is that you can't do that with physical access like PCI pass-through or SIOV. It's not possible to use live migration. Second is that if the hypervisor, for example, here crashes, all the VMs has to be restarted on the other hypervisor. There is no live migration anymore, and restarting a VM takes at least 10 seconds, sometimes more. It's not acceptable for our use case. So what we are working on right now is to duplicate protection virtual machines. So the VMA, with its protection service here, will be duplicated on the other hypervisor. Both are receiving sample values, both are calculating RMS, harmonics, and so on. And both are preparing goose message. But the cluster only allows one VM to send actual goose message. So it means the goose message on this VM are just not sent. They are preparing, but that cannot be sent to the overall network on the grid. And if something goes wrong, either on the hypervisor, on the VM, on the network, I don't know, we just have to open this gate here, and the goose message will be sent to the grid for the other VM. Right now, we are working on that in the worst case scenario, which means the hypervisor crash. Basically, we just unplug it and nothing works anymore. And we measure the time when we can still receive new goose message from these virtual machines. Actually, we are on a few seconds, and we are working on new technologies to reduce this downtime in the worst case scenario. And now I let Camilo talk about GE virtual IEDs.
Thank you. Okay, this is something that I like very much, and it is knowing the past to understand the present. Okay, so what we are talking about here is a very critical business, very critical business. Okay, as you understand, we are managing transmission, distribution. Well, our aim is to manage transmission, distribution, and generation, and that is a business that, I mean, it has started since we have energy. The energy started when Tesla and Edison invented the AC and the DC, right? Our company was founded by Thomas Alva Edison, the father of the DC. And when the power appeared, it was needed to have some devices to control the power. Okay, the power is not something that it is free, and you can take it, and you can take it for free, and if something happens, you have to be quiet. No, the power needs control, needs monitoring, needs a lot of things. Otherwise, they can kill you. Okay. So our business from the protection side started in nearly in 19s. So we started in GE. I mean, this business is managed by few vendors in the world. I mean, the main vendors, normally GE, ABB, Siemens, Schweizer in the US. Okay. Recently, 20 years ago, some Chinese companies started to appear. But this business is very, very traditional, as I said. So in GE, we invented the electromechanical relay at the beginning of the 20th century. Everything here was mechanical, okay, copper. When the current flows through the copper, it creates a magnetic field. The magnetic field makes one disk to rotate, okay, and that disk reaches one contact, and when that contact was reached, the real breaker was open. Okay. Then, mid of 20th century, the technology, well, the silicon appeared, okay, and our protection devices migrated to something that was done. I mean, all the algorithms here were done using logical gates, ANDs, ORs, nothing else. No microprocessor, no memory, nothing. Only ANDs and OR gates. 1980s or so, microcontrollers appears in the market. Okay, this is a device with a small microcontroller inside. In this type of devices, we started to program in assembler, nothing in C or C++. Okay, everything was done in assembler. Embedded in the microprocessor, a small display, 3 settings, that's all. Only one protection function was running here. Okay. Then, 1990s, the microprocessor appeared. In this case, we had like a small computer, okay, with a small micro. In this case, we had already memory, we had already some flash memory, etc. We were able to use C code here, okay, and all the algorithms were hard-coded in C code, downloaded to the microprocessor, and these devices were able to run multi-protection functions, not only one. Now we are in the 21st century. 6150 appeared. We are digitalizing the analog values into digital values with merging units. We have the latest generation of centralized protection and multifunction, multi-protocol, multi-communication, connection to the cloud, and so. Okay. Now we are in the stage where we are moving to something that it was running in a dedicated hardware. Okay, the hardware was designed by the vendor, in this case GE. Okay, that hardware so far was relying, and that is very important. We were relying on a true real-time operative systems, QNX, VSWorks, etc. Okay, now as we are moving to, thanks to Linux, and thanks that Linux is very mature nowadays, and thanks to the community and the real-time patches and everything, we are able to migrate from these commercial real-time operative systems. We are migrating now to Linux environments using real-time patches. okay? The criticality of our, I mean, we were reluctant 10 years ago, we were very reluctant to migrate from here to here. Why? Because of the criticality of our business. Okay, we have to be, when we change the technology, we have to be very, very, very careful, and that new technology has to be in somehow quite mature before deploying it in a real environment. Okay, because the power management is very, very critical for everyone. So now Linux is very mature. We have now replacing these real-time operative systems into Linux real-time operative systems, okay? And but still in the actual products, we are relying on FPGA technologies to do some critical and fast tasks, okay? For example, to calculate the RMS values when they come from samples. Okay, from the analog to digital converter, we have to calculate all the RMS values, the harmonics, the phasors, etc. Those specific tasks are still, normally, they are still done by this FPGA technology. What we are doing today is we are moving from something that it was very custom to a hardware to something that it is agnostic to the hardware. Okay, we are moving from a box solution to a software solution. Okay, and this is where we are today. We are today in the scenario of centralized protection and virtualized protection. Centralized protection is something that it is still very hardware. I mean, it has a lot of hardware dependencies. Okay, but with centralized protection, the customer is able to expand easily the functionality of the product. Okay, so centralized protection allows customers to expand the protection capabilities using a custom vendor closed hardware. Okay, this is like if you buy a MacBook, okay, and you buy one single, and little by little you install different programs. In the virtualized protection, it is the difference between centralized and virtualized is that the dependencies with the hardware, they disappear. Okay, we provide only software. That software will run in a server class hardware. Okay, it has to comply with some requirements in order to satisfy the real-time capabilities that we need. Okay, but the difference between centralized protection and virtualized protection is the hardware dependency. Okay, click on next. Next. This is the real deployment that we did in GE using SEAPATH. SEAPATH at the end is a hypervisor. Okay, it is nothing else. It is like Parallels in Mac. It is like VMware or VirtualBox or Hyper-V. Is that nothing else? The difference, VMware, Hyper-V, VirtualBox, etc. They are, let's say, proprietary. Okay, you cannot custom. It is as it is. Use it or leave it. There is no choice. In SEAPATH, it is something that you can achieve the same functionality than in Hyper-V, but you can achieve real-time performance. Today, with Hyper-V, you cannot achieve real-time performance at all. With VMware, the same. With VirtualBox, the same. With VMware, there is a release which it is called ESXi. Okay, they say that you can get real-time, and maybe it is true, but it is closed. It is a closed system. Okay, it is not scalable, and so SEAPATH to me covers all the drawbacks of the existing and commercial virtualization environments. So So SEAPATH, as I said, is a hypervisor, is nothing else. Is based. There are two releases. Well, two main branches of SEAPATH. One is a Yocto branch, and the other one is a Debian branch. Okay. In our experiment in GE, we decided to start with the Yocto branch. Why? Why not? Okay, that's a quick answer. Yocto, let's say, gives you freedom, more freedom to custom, okay, if you need to custom something. At the end, a hypervisor is something that has to be very, very light. Okay, all the power and the intelligence and the IP remains on the virtual machine. The hypervisor is only a virtual machine manager. It has to do nothing else. Okay, so Yocto gives you the possibility of make the hypervisor very, very light to comply with your requirements. Okay, but there is also a branch based on Debian. Okay, and we will test. We will start testing the branch in Debian very, very soon. So the area in gray, it is SEAPATH. Okay, all the area in gray, it is SEAPATH. This is this box is the hardware. In this case, we are using a hardware with 24 cores, 64 gigas of RAM, 512 gigas of hard disk. The hardware is the less important thing. Okay, there are plenty of hardwares in the market, Advantech, Velotech. I mean, we have to be agnostic. If the customer, if RTE or Alliander or any other customer, they have certified Hewlett-Packard, just to see something, as the server where they want to run the system. Okay, fine. We will install SEAPATH on the Hewlett-Packard and all the things that we need to run SEAPATH. In our case, our hardware had 4 physical ports. This is external to the server, so we deployed one Ethernet LAN for the process bus. The process bus is in charge of collecting the sample values through merging units. And we prepare another network for the station bus. The station bus doesn't need real-time requirements normally. Okay, the process bus, everything that it is flowing through the process bus, it does need real-time requirements. And as I said before, we have to parse values every 250 microseconds. And it is not only a matter of parsing 1 kilobyte of data every 250 microseconds. We have to parse sometimes 500 megabytes of data, 500 megabytes of data every 250 microseconds. Okay, very few systems are able to do that. Very, very few. If you are not able to do that, you are losing data. If you are losing data, you are not able to monitor the power properly. Okay, it is very, very important to not lose data. So all the analog waves for currents and voltages, they are digitalized through merging units. The merging units converts the analog values into digital values. The digital values goes to this physical interface. Okay, this physical interface goes to the virtual interface, and these boxes in blue are the virtual machines. This is where the power is. I mean, the power in terms of intelligence. Okay, this is where the intelligence is. Each virtual machine is an independent operative system. With applications inside. Okay, you can deploy the applications using containers, using standard applications without isolation, etc. Okay, so in our case, we need real-time capabilities. So our operating system has to support real time. So in this case, we call it a test VM. What we call test VM is a virtual machine that it is capable to manage real-time requirements. So in our case, we deployed a Yocto Linux here, another Yocto Linux, okay, different from the Yocto that we are running in SEAPATH. SEAPATH, again, is the hypervisor, nothing else. On top of that hypervisor, what we did, as you do with Parallels or with VirtualBox, you select the .iso file or the Q0222, deploy the virtual machine, and that file has inside, is a single file that has the operative system and, well, and maybe nothing else, okay? Because all the applications can be deployed after you deploy the virtual machine. So you deploy the virtual machine. In our case, it was a Yocto-based virtual machine. We have another operative system running on SEAPATH, okay? As it is a virtual operative system, we have to virtualize the hardware. So this is a physical interface, and this is a virtual, we call it a logical interface. Okay? To transfer the data between the physical interface and to the logical interface, as Erwann told you before, we are using pass-through. We tested different technologies here to transfer data. This process is very, very critical. This is where we are passing 500 megabytes of data every 200 microseconds from the real side to the virtual side. So we cannot lose data here. Okay? And the best technology, after testing a lot, several technologies, was the PCI pass-through. Okay? All the data goes to an application that it is in charge of reading those digital values. We call it in our environment sample values. Okay? Reading those sample values, we are calculating the RMS, phasors, the harmonics, etc., and we are publishing the data in a broker. The orchestration inside of this operative system, which it is virtualized, the orchestration of the applications. For the orchestration of the applications, we are using Docker. Okay, so every purple box that you see here is a container. Inside of every container, you have different threads. Okay, so the very first thread is to parse the data. We have different threads, as I said. Once we calculate the RMS values and the phasors and so, we publish the values in a broker. Okay, and this is where the protection algorithms are collecting this data as an input. The protection algorithm executes whatever it has to execute, and the protection algorithm is the one that decides if the power is stable, if it is needed to trip, if it is not needed to trip, etc. Okay, the rest of the blue boxes are another virtual machines. This is a Windows operating system, just to, as an example. No? This could be another Windows operating system, Ubuntu. You can deploy here a Debian. Those are the Sonoma from Mac. It is completely open. Okay. So the main idea here is how do we move from something that was very hardware dependent, okay, to something completely new, in a sense that, in a sense of we are creating a virtual machine, okay, we are creating a hypervisor with real-time capabilities to guarantee the real-time requirements that we need in our domain, okay, in our business. Some other businesses, they don't need the real-time capabilities that we need. That's why they can use VMware, Hyper-V, and those kind of systems. In our business, no. In our business, we need very true and very determinism system. Okay, we are managing data every 250 microseconds. That is very tough. That is very, very tough. Okay. And yesterday we did a demo. Next. Yesterday we did a real demo to show you the real performance of this SEAPATH system. We were not allowed to show the demo again, but I am showing here three scenarios. So in the first scenario, what I am showing is we inject the analog value with a machine. The analog value is converted to a digital value. The digital value goes to SEAPATH. SEAPATH does whatever it has to do, okay, to see if the power is stable or if it is not stable. When the power is not stable, it has to generate a message. The message goes to the well. This message is a digital message, of course. It is a digital message. This digital message is converted in a mechanical message in a sense that we are closing one physical contact output, okay, and we stop the timer when we close the physical contact output, okay, and the round trip for the whole process was 7 milliseconds. Okay, I don't know if that tells you something, if that is quick or that is not quick for you, but normally the conventional protection, the conventional relays, which are very hardware dependent, normally they trip 12 milliseconds. Okay, so we are even, I mean, but as Erwann said, in terms of be fast or be slow, we have to comply with certain requirements. Okay, it is not very important to trip in 7 milliseconds. 12 milliseconds is also okay. The most important thing is that if you repeat the test 8,000 times, okay, you have to obtain 7 milliseconds or 12 milliseconds 8,000 times. Okay, it cannot be random. It has to be, okay. That is what we call jitter. How much is the deviation versus the nominal value. In the scenario number 2, that you see that we are acting faster. We are acting faster because we are removing the digital to mechanical, let's say, conversion. Okay, because at the end that is something. This mechanical conversion, it is something that we cannot control. It depends on the physical device that you are using to convert digital to mechanical. Okay, Siemens has one, GE has one. Siemens maybe it is faster than us. I don't believe so, but could be. So in order to be agnostic, okay, to that conversion, we prepare the second test, and in the second test we are generating, we are detecting here the disturbance in the power, okay, but we are not converting to a mechanical contact. We are stopping the timer when we send the digital message, okay, and the time is what, 4 milliseconds, okay, and the third test is even, we are eliminating some more noise. The noise that we are eliminating in the scenario 3 is that we are not using this step. This step is a machine that generates the analog value and it converts the analog value to digital value. Okay, so we said, okay, let's make the same test, assuming that I start the timer. I start the timer when the sample value, when the digital value is already in the network. Okay, and I stop the timer when I detect the disturbance in the power. Okay, so in that case, SEAPATH is able to SEAPATH with the virtual machine is able to detect that disturbance in 2 milliseconds. Okay. That's it, I think. Well, this is very quick. I mean, nothing is magic. Okay, we applied a lot of intelligence, a lot of testing, etc. This is a picture of how we manage the CPUs. I mean, the CPU affinity is very critical. It's very critical here. Okay, so when you see here minus something means that that core, that CPU. I mean, we are using a server with multi-core, with 24 cores. When you see here a minus something, that means that that CPU has very high priority, very high priority, okay, when executing something. If you see something positive, okay, plus something, that means that the CPU has low priority, okay? So in our case, you can see that most of the CPUs, they are, I mean, they are stressed. They are working as very quick. Okay. For that scenario, we are using 6 cores out of the 24 that we have in our server. So the real-time protection machine is using six cores. Okay. With 6 cores, we are doing all the things that I explained before. Creating the hypervisor, taking the data, detecting the disturbance in the power, generating the data value, etc. And that is a graphic of how the load in the CPUs are distributed. So if you see the CPU number 3 is reaching 100%. The reason for this is that CPU number 3 is in charge of executing all the protection algorithms. Okay, so that CPU is 100% dedicated to monitoring if everything is going well when they are getting data from the power. Okay, the other task that it is taking a lot of consume is CPU number 4. CPU number 4, if I remember, CPU number 4, yeah, the CPU number 4 and number 1, they are dedicated to parse all the data that we are receiving from the physical NIC, which it is 500 megabytes every 250 microseconds. Okay. Okay, nothing. That's all.
Thanks. If you have some question now, we can answer. Yes?
Did you also consider a master-master setup where you have 2 virtual IEDs that both receive all signals but also send out gooses?
This is possible. The question relies on the end of the user at the end, so the person managing the substation. Is it okay for all the devices in the substation to receive two times exactly the same goose message, or is it not? As I understood, many times it's okay, and you don't have any problem in that case because everything works fine, but in sometimes it could be not, and we have to think about a way to resolve the problem where it's not possible.
Did you consider building a line differential protection regarding the jitter and transmission delays? Did you consider building a line differential protection with this, regarding the potential jitter in the transmission of the measurements? Line differential protection, yeah.
Yes. The aim of this platform is to cover transmission, distribution, generation, and to do that, we have distance, line differential. I mean, all the protection functions that you have in the conventional devices, we are porting everything into SEAPATH. Yes. Of course.
Sorry, the time interface is normally by the manufacturers today between two protection devices if you make line differential protection. Do you think you can use normal TCP/IP connection?
So normally the line differential protection is a proprietary interface right now. Yeah.
Line differential is because you have two ends, and this I didn't think about that. We have to think about that. That's a very specific. That's a very specific scenario that we have to think about that. How do we manage that line differential protection?
Sorry. No, I have two.
Questions? Thank you, danke.
Listo.
Thank you.